All right. So this is what we sort of left off on last time, and we were talking about the heme group in something like a hemoglobin, etc. This specifically right here is this heme group, which is one of the possible heme groups that could exist, right? This one being the human one that we were concentrating on. That one being the important one for us being humans, nominally. Okay, so anyways, these are the pyrrole rings right here. You may recognize them actually from organic chemistry. They were a fairly common nitrogen heterogeneous ring that we had talked about, but it's okay if you don't. There they are, ta-da. Here's the iron. Now, one of the things and reason I'm sort of starting on this right here is because I need you to look at this and go, hey, that has 4 nitrogens attached to it. Okay, everybody good with that so far? Okay, so that iron that lays in the middle there has the 4 pyrrole nitrogen atoms, as we just saw in the diagram. The iron can actually form 2 additional bonds. In fact, iron of that charge typically forms 6 bonds to it. And they are usually considered pseudo-covalent bonds, by the way, because the transition metals have enough electronegativity that they can form covalent bonds. Okay? Now, the 5th coordination site, that's the sites on a metal that you're forming the sort of pseudo-covalent bonds to. Okay? That's going to be occupied by an imidazole ring. This is typically from the histidine residue, especially in something like a hemoglobin or such. And this is going to be from the protein, and this will be called a proximal histidine. Think of it as part of the protein stretches back around, so back around, comes up from below, and has that histidine form a bond right there. Okay? Is that making sense so far? Did everybody get confused or no? Okay, so this is the proximal histidine. The 6th coordination site is typically going to be left open until you bind an oxygen. Okay? Now you may wonder, hey, Dr. Clausen, when we're not binding oxygen, don't we have an open reactive site that things would bind to? Anybody wonder that? Yeah. Fantastic. And you're right. And there's things that we can do to keep that site from getting at. Okay? And we'll get to that in just a bit. So the deoxymyoglobin, myoglobin being another thing that has the hemoglobin, that being the single unit, a little bit tighter bound than the normal hemoglobin. Okay? So myoglobin having a heme group. Myoglobin is in its free, oxygen-free form. This would be the deoxymyoglobin. Iron is going to be the iron Fe2 plus oxidation site. The iron is going to be too large to fit into the hole within the porphyrin ring. The oxymyoglobin, on the other hand, the myoglobin is going to be oxygen bound. When oxygen binds the iron in that heme, the iron is going to move into the plane of the protoporphyrin ring. So what happens here? On one side, you have a histidine sucking it down, right? So you have that histidine sucking it downwards, okay? Remember, this has 3 dimensions to it, okay? And what's going to happen is when you bind it with an oxygen, the iron is going to move up into the ring. When it's not bound to the oxygen, it's going to move down below the ring, okay? This is going to reduce iron's ability to bind oxygen, meaning that the oxygen can be released easier, right? Okay. Now remember, when we're looking at these things, do we actually want the oxygen to bind so strongly it never releases? So what's the purpose of something like myoglobin? Is it to bind oxygen and never release it? Oh, it's to carry oxygen, right? Yeah. It'd be really bad. Like, would your hands work very well if every time they attach to something, they're never detached? No. So the myoglobin has to have a happy medium. And this is a very common thing in biochemistry, okay? This is how a lot of biochemistry works. is it's a happy medium. Okay? It binds well enough to hold the oxygen until you get an environment where you don't have a lot of oxygen, in which case the oxygen comes off easily enough. Right? If it binds it too well, it's not going to work well. If it binds it too poorly, it also isn't going to work well. Okay? All right, and this is a great demonstration of this. So right here we see the deoxymyoglobin. This is the proximal histidine, by the way, right there. And we can see that it sucks it a little bit below that ring, right? This is the porphyrin heme group here. Okay? And you can see it's a little bit sucked below. This is going to cause things to not attach quite as easily, right? Okay. And so when oxygen attaches to this, it's going to suck it up into the ring. This is going to make that less energetically favorable to attach that sixth position than it otherwise would be if we did not have this proximal histidine here. This is the oxymyoglobin, by the way, that we would talk about. Obvious since you see the oxygen probably, but you get it. Okay, and that attaches to that sixth coordination site. Does anybody have any questions about that so far?
So when the iron is lower, it's because things don't attach as easily and
Yeah, so there's two ways to look at this. It being lowered down there makes it less energetically favorable to attach, so it's not quite as good at attaching things. On the other hand, when you do attach things, it has to pull it up. And that's why it's not as good, is because it has to provide that extra energy to pull it into the ring, right? Yeah. Does that make sense? I know I kind of like sidestepped the direct answer there. But, yeah. Now let me ask you a question. Hey, this doesn't attach to anything. Where's that histidine? Is it just freely floating, do you think? No, it's attached to the protein, isn't it? Okay. What would happen if we pulled that histidine further down? If we don't allow that histidine to move upwards? Can we attach oxygens to it? We're going to block that oxygen attaching. We're going to make it less favorable, even more so less favorable. Okay, so this right here, the oxygen binding to the iron in the heme is going to be accompanied by a partial transfer of electrons to this ferrous iron right here. Remember, it has a 2+ charge. It's being stabilized. What's going to happen actually is iron can take on the 3+ charge. Oxygen's electronegative enough, it would normally oxidize iron, right? And what happens to blood if you leave it out with oxygen on it? It oxidizes. Yeah, it oxidizes the 3+ charge and it starts looking like rust, right? Yeah. Yep. Okay, so we're actually kind of pseudo-oxygenating it, okay? We're oxidizing it, but not quite. And that's what our porphyrin ring and our heme group is doing for us. It's attaching it tight enough that it's going to have difficulty doing that reaction, okay? And so again, yes, we attach it to the coordinate site. This is actually going to form an equilibrium between the superoxide ion and the neutral one. The superoxide ion is the 3+ charge. There's two reasons why it's critical that oxygen is released only in the O2 state, not the superoxide state. So if we release this in the superoxide state, where we have a negative charge to it, does that look stable? No. After your experience with organic chemistry, you probably are going, oh, that'd be bad. This would be very reactive, right? Yeah. So superoxide is very reactive, is very damaging to many biological materials. It will react with most of your structures you have in cells. There's actually not that many that would not react with. Iron would be left in the ferric Fe3+ state. This would actually prevent it from binding any additional oxygens because it would then be in the iron 3+ state. It would also change its binding to the protein and heme group, okay? Which would change the protein considerably. Metmyoglobin is myoglobin that's bound to the iron in the 3+ state. And you can see that it even has its own naming, right? Metmyoglobin. All right. So again, this is that binding pocket for your myoglobin. It's going to include one more histidine that we have to talk about. Remember, below the iron is the proximal, right? Above here, not attached to the iron, is the distal histidine. The distal histidine is going to stabilize that oxygen. So it's actually going to donate a hydrogen bond from this imidazole group to that bound oxygen here, which is going to help to stabilize the bound oxygen in this form. Okay? And that's going to help you keep that from releasing superoxides. Otherwise, this actually would be an effective enzyme to make superoxides. Which would be interesting, huh? All right. So carbon monoxide, on the other hand, why that's an issue. It's a potential competitor for oxygen binding of your myoglobin. Studies actually suggest that myoglobin has evolved to show enhanced recognition of oxygen versus carbon monoxide, but it is limited by a much higher intrinsic affinity at 4 carbon iron to carbon. So carbon actually has better affinity to the iron, but the structure of our myoglobin actually does counteract that to some degree. So carbon monoxide should be much more poisonous than it actually is to a human or an animal. Okay? Again, this is it binding in that binding site right there, and that's the carbon monoxide right there, and you can see the carbon. And part of the problem is that carbon monoxide actually forms a better fit for a bonding with iron. Yeah. Okay, so the hemoglobin has to bind oxygen in the lungs, and then it's going to release it as much oxygen as possible to your tissues, specifically to where you'll have the least amount of dissolved oxygen, right? So the hemoglobin is going to consist of 4 myoglobin-like subunits. We're going to have 2 identical alpha chains, 2 identical beta chains. So you have 2 different types of subunits, but you get 2 of each of them. Okay? So you'll have an alpha 1, alpha 2, beta 1, beta 2, right? The hemoglobin tetramer, tetra 4, so there's 4 subunits being joined together, is a holodimer of heterodimers. Does that make sense? Okay, so if you split them into 2, you can have 2 structures that are the same, right? And then those 2 structures, though, are then heterodimers, okay? Because they have an alpha and beta subunit. Did I lose anybody with that? No? All right. Okay, so again, you're going to have a pair of identical alpha-beta dimers. That'll be alpha-beta 1, alpha-beta 2, right? Or alpha 1, alpha-beta 2, 1. Each of these subunits is going to have a set of alpha helices in the same arrangement as the alpha helices in the myoglobin. And that's the myoglobin-like portion, though the beta isn't that different either. The structure motif is actually called a globin fold. And so right here, we actually see this in a ribbon structure, which makes it easier to see. The reddish colorings are alpha. The beta is the yellowish colorings. And you can see they're sort of opposite sides of each other. Can everybody see that okay? Okay. Each of these subunits does have its own heme group, though. So you have a total of 4 heme sites. Okay. And again, these are the exact same. We just designate them 1 and 2 because we want 1 and 2. So we can differentiate the 2 sides, right? Okay. The split would actually be right here in case you're curious and didn't immediately see that. Okay. By the way, anything interesting about that structure? So you got little heme pockets, right, that can let little things in. You can see these 2 because they're towards you. But you have basically the same thing on the other side as well, right? All this is like one hand and then the other hand on top of it. Okay? Look at each side. All right. Notice this space here. There's a gap, isn't there? Yeah. So this structure can actually twist and change. And you can shove things into that gap. Okay, so hemoglobin's kind of interesting, and what makes it have its special properties where it can transport oxygen to low oxygenated areas in your body is that it actually binds oxygen cooperatively. So the hemoglobin is going to exhibit a sigmoidal oxygen binding curve. Remember, sigmoidal is that S-looking curve? Okay. This is going to indicate your oxygen binding or release at one site within the tetramer actually is going to increase the likelihood of oxygen binding or release at another site. So when you bind your first oxygen, it actually becomes even more energetically favorable to bind the next oxygens. So if you get a hemoglobin binding one oxygen, it's probably going to fill all the sites. Okay? And if it releases one oxygen, it becomes more favorable to then release the other ones. Okay? And that's cooperative binding behavior. The cooperativity allows the hemoglobin to bind oxygen in your lungs where it's very plentiful, and so it fills up really fast, right? And then when it gets somewhere where it has difficulty to binding oxygen, where it's very low concentration, right? It's then going to release the oxygen very rapidly. Okay? Anybody have any questions about that so far? Hey, wait a second. Does that mean that my best oxygenated areas in my body would have direct connections to my lungs? And then anything past that would actually have a much lower oxygen level? Does that work out in reality? Okay, so my head, direct connection. My middle body, direct connection. Up here on my shoulders, direct connection. Thighs, pretty direct connection, right? What happens when I get down to my fingertips? Yeah, we start seeing more blue, don't we? Which is the deoxyhemoglobin, isn't it? Yeah. And so, hey, we can prove that right here, right now, can't we? Cool. Okay, so this right here is actually the binding curve for myoglobin and hemoglobin. What do you notice about myoglobin's binding curve? That's just straight up logarithmic, isn't it? Yeah. That's not sigmoidal for myoglobin, is it? What do we notice about hemoglobin's binding curve, on the other hand? That's sigmoidal, isn't it? Okay? And that's because, again, as you start binding, as soon as you start binding the one site, it quickly binds all the others and maxes out. And vice versa. You start losing, you lose faster. So the P50 for the hemoglobin is 26 torr, which is considerably lower pressure than the P50 for myoglobin, for example. Okay? And so what ends up happening is they can work as a pair. Hemoglobin takes up oxygen really easy, but loses it a lot easier than myoglobin, right? Myoglobin, on the other hand, will strip the oxygen from hemoglobin usually. Okay? And then it will concentrate the oxygen in the area and release it slowly over time. Okay? Does that sound like a behavior you might want in your muscles? Or for like a baby? Yeah. Guess what a baby typically uses for its oxygen carrier? Myoglobin, right? Yeah. Okay. So again, you have that cooperative binding. Right here we can see the tissues and lungs levels of oxygen. And this cooperative binding in hemoglobin actually gives you a pretty efficient oxygen transport. Honestly, 66% is no joke. That's a really good number. Unfortunately, humans have terrible lungs, so it doesn't really work great for us. Birds have much better lungs, right? And very similar hemoglobin structures. Anyways, this right here would be myoglobin, which has no cooperativity, right? And so what we get here is this would be the PO2, the partial pressure of the oxygen in the tissues. Right here is the partial pressure of the oxygen in lungs. See, the oxygen in lungs about 5 times that of tissues. Okay? And so if you trace these across on these curves, that gives you the amount of oxygen that you would release when going from the lungs to the tissues, right? So what we can see here is myoglobin, if we were to use that to transport oxygen from your lungs to your tissues, you would only transport 7% of that oxygen that you take in any given breath. Okay? That would actually only be so these numbers actually would represent the oxygen that you would actually bring in and absorb through your lungs. Okay? But this would be the 7% of the oxygen available to the lungs would be delivered to the tissue for myoglobin, right? Which is not very good, is it? No. What if we had hemoglobin? Well, hemoglobin has a sigmoidal curve. It has that cooperative binding. And so we can see it's a 66% release to the tissues, which is the vast majority, right? The greater majority, I should say. That's the official term. This would be a hypothetical hemoglobin with no cooperativity. And so it has a logarithmic relationship, but doesn't bind it as well as myoglobin. Okay? And what you can see is with no cooperativity, you would get about 38%. So, I mean, better than myoglobin, but not as good as cooperativity, right? Considerably worse. Okay, so this also allows you to deliver tissue, or deliver lungs to the tissues that need it the worst. So what happens is, as you deliver oxygen, the partial pressure is going to go up unless you're utilizing that oxygen, right? So in the tissues at rest, you're going to see an PO2 of about 40. Now, because this sigmoidal curve has such a rapid drop-off right in that region, what you're going to see is that you only end up releasing about 21% of your oxygen from your lungs to that tissue. Okay? Whereas on the other hand, if you are undergoing exercise, running or something, then that remaining 45% is going to end up being released there. That's because during that process of exercise, you're consuming that oxygen in the area, right? And you're lowering the partial pressure of the oxygen. Okay? And if you were to lower it even more, you would get even more released, wouldn't you? Until this point right here. In which case, you've maxed out. Yeah. Okay. Anybody have any questions about that? Okay, so there are 2 major states for hemoglobin that we need to talk about. There is the 10th state, which is the T state. This is actually the quaternary structure of deoxyhemoglobin. So that deoxyhemoglobin, where the iron had been pulled out of the ring, remember, down out of the ring? Okay, that's the 10th state. The R state, which is the relaxed state, is going to have a quaternary structure of the oxyhemoglobin. That means where the iron has been put into the ring, where it has been pulled away from that histidine. Okay? That has been pulled into the ring. So in the R state, the oxygen binding sites are going to be free of strain. They're going to be capable of binding the oxygen with a higher affinity than your T states. Because remember again, your T states is where you are in the structure of the deoxy. To bind the oxygen, you have to go into the R state, right? To unbind it, you have to go into the T state. Okay? Okay, so an oxygen binding, the A1B1 dimer, is going to rotate 15 degrees relative to the A2B2 dimer. So remember how I said it's like your hands being put on top of each other, like you're grasping them, okay? So when you bind an oxygen, it's actually going to rotate your hands, okay? And when you unbind them, release them, it's going to rotate them back. So your binding of your oxygen to one side is going to increase your binding affinity to your other sites by triggering that shift from the hemoglobin tetramer from that T state to that R state. It's actually pulling your entire protein is actually changing configurations from the T state to the R state when you bind an oxygen. Okay? This shows you the figure statically. So this would be the deoxyhemoglobin right here. When you bind oxygen, it's going to rotate 15 degrees. See that gap there? Remember the hole that we talked about right there? See that? Okay. So when you rotate 15 degrees to the oxyhemoglobin, that hole actually closes. Okay? And it will squeeze that hole. Again, the T and R states refer to the ability for the iron to move. Keep that in mind. Okay? So the tense state, the iron can't move up into the ring because it's tense, getting pulled, which is this state here. Okay? Relaxed state. When we're in the relaxed state, we're going to have it so you can move the heme group, right? The iron in the heme group. Okay? Funny enough, it actually works pretty well in your hands too if you want to try it. So if you close your hands normally where they're relaxed, they won't have much gap in between them. If you then rotate them 15 degrees to be tense, you get a bigger gap. So it kind of works, which is kind of weird, but I find that sometimes it helps to tactically feel that, right? Anyways, the hemoglobin is going to cooperatively incorporate aspects of two limiting models. That's the concerted model and the sequential model. So in your concerted model, the overall assembly can exist only in the T state or R state. The binding of the ligands will shift the equilibrium between these two states. So you can think of it like this. This is a great demonstration of this. So here we have equilibriums that will exist between each T and R state. This would be the T state with nothing bound to it. This would be the R state with nothing bound to it. T state with one oxygen bound, R state with one oxygen bound. Everybody getting that okay? Fantastic. So when you have no oxygen bound, the T state's going to be strongly favored up here. Okay? And so your equilibrium between these two, the T and R state, will favor the T state strongly. When you bind an oxygen, this lowers that affinity towards the T state and increases the affinity towards the R state, right? And so what's going to happen is the equilibrium will start shifting towards the R state. Okay? And then when you bind the next oxygen, which is now more likely, isn't it? Because your equilibrium favored the R state, you're going to further favor the R state. At this point in the middle where we have two bound, this is sort of your 50% point. Okay? This is where your equilibrium tends to be not as highly favored to either form. 3 oxygens, at that point your R state is actually going to be the favored form. And 4 oxygens, you strongly favor the R state. Okay? Is that making sense okay? Okay. Now, keep in mind we also have equilibriums that exist for the oxygen binding, don't we? Okay? And as you can see, when we favor the R state favors that oxygen binding, doesn't it? But what happens? Well, remember that an equilibrium exists dynamically, right? So when we go somewhere that has lower partial pressure, we're going to lose an oxygen every now and then. Because even though the equilibrium favors one side, there's still some of the other exists, right? And so when we lose that oxygen, if something doesn't come back on there, we slowly start progressing and it becomes faster and faster to lose the next oxygens. Okay? And that's that cooperative binding we had talked about. Okay, so this is right here, the observed hemoglobin binding state curve. So right here is that sigmoidal one we've been seeing. Okay. This is actually the binding curve for the R state, and this would be the T state right here, right? You can see the T state's actually so poor at binding oxygen that we don't even see, we only start seeing where it starts capping off up here, don't we? See that? It almost looks linear. Because at this point, we're in this section right here. We're not seeing the nonlinear behavior yet. So anyways, this right here is the R state. It would be so good at oxygen binding, it basically looks like myoglobin, right? Yeah. And then the observed behavior is this sigmoidal. And that's because the the two tetramers, two dimers that form a tetramer, this can rotate, giving you a mixture between the R and T states. Another way of saying that is we're seeing these two curves mixed together to form the sigmoidal curve. Okay? Did that make sense? Okay. Yeah, what we're seeing here is we're seeing the equilibrium between these two curves here. Okay? And if you were to, say, fix the hemoglobin into the T state, you would see this curve here, right? Which would greatly reduce the amount of oxygen being uptaken. Okay, so this is the sequential model that's the next one. So our sequential model, the binding of a ligand to one site in an assembly increases the binding affinity of the neighboring sites without inducing a full conversion from the T into the R state. So this is a different model to think about this with. The first one was the concerted. The next one is the sequential. Okay? All right. So right here, what we're seeing is we're seeing the T and R states. If you forgot your labeling here, the T state is square. The R state is circular. Because apparently, well, squares are tense, right? I guess. We're going like 1960s slang, right? You're such a square because you're so tense. Anyways. Okay. So in a sequential model, when you're fully tense state, you'll be in this form right here. When you bind an oxygen, remember, oxygen is not favored to bind, so your equilibrium favors the tense state at this point. Okay? What's going to happen is you're partially going to convert to the relaxed state. And so you'll slowly start converting, little bit by little bit. When you can partially convert to the relaxed state, this is going to increase your affinity for oxygen, and your equilibrium is going to shift to favor more binding, though still favoring the tense state. Okay? And so then you'll get your next binding, and at that point, you'll have an equilibrium that doesn't really favor it either. Okay? And then you get your next binding, and that favors further binding, doesn't it? And at this point here, we'll be sort of half T, half R. And then we'll favor the R state more, and we'll be more in the R state, and then we'll fully be in the R state. Okay?
So in the conservative model, basically can be
Either or, yeah.
either or.
Yeah.
And then, but it just sticks that way.
You never have like a half T, half R.
Yeah, but in the
You have half of your population is T, and half of your population is R. Think of it a bit like definitions. So you can have a open or closed hand, right? Okay? And that would be like the concerted model. Okay? So we have open or closed, and that determines whether we're moving the thing. Okay? In this, we can have a partially open, partially closed. And that partially open, partially closed determines whether you're holding on to something or closing it. It's just a different way of looking at it. Does that make more sense? Yeah. All right. Fantastic. So the hemoglobin behavior, neither model really fully accounts for the behavior of hemoglobin, to be honest. That's why we typically tackle this in a dual model system here. So the hemoglobin behavior is concerted. The tetramer with 3 sites occupied by the oxygen is almost always in the quaternary structure that we would associate with the R state. And so when we look at this, it looks very R state. The hemoglobin is sequential though, because the hemoglobin with oxygen bound to only 1 of 4 sites actually remains primarily in the T state. And so we don't actually get a shift over into the R state. So neither model is fully encompassing what's actually happening. It's probably some weird combination of the 2 models that you would need to use. So the transition from the deoxyhemoglobin T state to the oxyhemoglobin R state occurs upon the oxygen binding. When oxygen binds the proximal histidine, remember that's the member of the alpha helix, is going to move with the iron ion. The carboxyl terminal end of a helix lies in your interface between the 2 alpha beta dimers. Okay, so what does that mean? Remember the histidine? Let's go back. Okay, so really quickly, the terminology you need to remember from here is going to be the proximal histidine is attached via an alpha helix, will move with the iron ion. Okay? So what we have is the iron ion is attached via a rod to that proximal histidine, right? Okay. So when the carboxyl terminal of the helix lies in the interface between the 2 alpha beta dimers, so the helix has a carboxyl group that lies in that interface that closes and opens when we go from T and R state, right? The structural transition at the iron ion in one subunit is directly transmitted to the other subunits. So think of it a bit like this. When you bind an oxygen to that heme, it's going to move a rod, which will then move that carboxyl group, okay? That transition of the carboxyl groups is going to change the structure within that gap. When you change the structure within that gap, it's going to move that, right? Does that make more sense? It's a very mechanical process, a bit like a bike or something. That's going to end up favoring your T to R transition, which is why your equilibrium shifts as you bind more oxygens to favor the R state, right? Did I lose everybody? Yeah? I lost everybody? Okay, is anybody lost? Seriously. All right. Okay. So a good way of thinking about this is if we go up here. There we go. Oh. Okay. There we go. All right, so I'm going to have to sort of use several figures to help you fully encompass this, but we're first going to remember proximal histidine, okay? Okay. So right here, we have our proximal histidine bound to our iron, right? Okay. We have abstracted our protein so that we can sort of see this region. Remember, we won't be able to see this region if we looked at the protein. It's big, bulky, and difficult to see through, right? So what we have here is, this is our interface gap, okay? This is the alpha 1, beta 1 coming together with the alpha 2, beta 2. Okay? Our 2 hands coming together, right? Within that gap, we have this interface right here. And so what we're going to see is that this right here in the red is the oxyhemoglobin, i.e. the R state, right? And you see how you've actually caused this because of this relaxation right here to actually pull back. See that? Okay. Like a little spring, right? And this is I mean, really, basically, this is a spring-loaded histidine. It's a spring-loaded heme, okay? So you got the iron here. It has a little spring to it that pulls on it, right? Okay. And so when you relax and cause this gap to close, it's going to cause this to move up into the ring. Okay? When you go into the T state, this is going to cause this gap to open, and it's going to cause your spring to pull. Okay? And that's going to pull that iron out of the heme downwards, right? Can everybody see that and envision that okay? Okay, so R state, T state. Okay. By the way, the red oxygenated blood. Red, yeah. And so you pull this direction, gap closes. It's going to relax the histidine so that you can pull it up into the ring. Okay? Gap open, it pulls that histidine down and makes the iron pull away from the ring, right? And that means you can't load it anymore. Okay? It actually works a bit like a clip on a gun, which is kind of weird, but whatever. I guess similar principles. All right. This actually shows, again, another figure demonstrating the same sort of information. And so right here, we actually see that movement of the histidine here. And this is going to be what drives cooperativity, by the way. So when we bind one of these, it's going to cause it to go more into the R state, right? Which is then going to relax this pull here and allow more oxygens to more easily bind. Does that make sense so far? Fantastic. Okay, excellent. Okay. Mm-hmm.
Like, why is the second one for me so much?
Okay, so once we've, so this one right here shows you that difference in the gap. So in the R state, this moves upwards. In the T state, we see how much you have to extend that bond up, which is going to put a lot of stress on the bond, right? So like a loaded spring. Does that make more sense? Yeah, and that's why the bonds are there and they're not there. Because you actually wouldn't have a bond there anymore. You'd start breaking it at that point. Yeah. Okay, so now that we've discussed how you can actually have that, when it uptakes oxygen, you're going to want to be in the R state, right? And it'll transition to the R state. What happened, so let's say you don't want a gun to fire, you don't want a spring-loaded thing to fling stuff out. What do you do to the spring? So you could take it out, but that would wreck it, right? You have to reassemble. What if you put a little rod or something in there and held the spring? Yeah, that would work, right? Okay. Guess what our bodies do when it doesn't want hemoglobin to load up or it wants it to release more? Yeah, throws a rod in there. And that's what we're going to start talking about. So this is 2,3-biphosphoglycerate, typically just referred to as 2,3-BPG, because biochemistry, these names get really long. We like to shorten them a lot. Okay? If you ever make or read a publication, don't start off with the abbreviation. Okay? The first time you use the abbreviation, you should always state it fully, and then you can use the abbreviations. Because it very quickly becomes confusing. All right, so this is going to stabilize the T state of the hemoglobin. It's going to facilitate the release of oxygen. It's going to bind in that pocket of that hemoglobin tetramer that's going to exist in your hemoglobin T state. This will actually block it from assuming the R state with that still bound, right? So to assume the R state, you would actually have to unbind. Okay? This is an allosteric effector because it does not bind within the binding sites. Okay? So the oxygen heme binding sites, this never goes near. This binds down in the gap. Okay? It does, but not directly. So it never goes here. Okay, so let me just define allosteric, and I'll go back to the figure real quick. So an allosteric effector is an important definition that you'll need to know from now on. And this is something that binds, that affects the binding of another molecule from a distance. It doesn't do it at the binding site where you'd have the binding occur. Okay? Okay. So let's look at the figure up here. There we go. Okay, so these are the binding sites. An allosteric effector will not go to the binding sites. The 23BPG doesn't go to here. It binds right there. Right here. In the gap. And that's going to block you going from the T to the R state, right? And thus, it's going to lower the affinity in the binding sites for that oxygen. In fact, it's going to be very hard for that oxygen to bind at all because you're pulled out of the ring, right? Well, it will only lock it into this T state. Yeah. It can't get in here for the R state. Okay? Or another way of saying that is if it actually came in here and successfully started binding, it would force this open. Exactly. A bit like water forces salt ions to come off. That binding energy is going to do that. Exactly. Exactly. You bind at a different spot than the binding site, and yet it affects the binding site. And yet it affects its binding and function of the enzyme or protein. Oops. Where the hell did I? There we go. Okay. So right here, this is the oxygen binding by pure hemoglobin when we can compare it then to the hemoglobin in red blood cells. And so right here we see the oxygen binding of pure hemoglobin without the 23BPG. It has a sigmoidal curve, but it is significantly less than the hemoglobin in red blood cells where you would have 23BPG. Okay? So this presence of 23BPG causes this sigmoidal curve to shift over this direction, lowering the affinity, i.e. shift into the pocket we actually want it for that oxygen partial pressure difference between the lungs and tissue. Okay? That's another way of saying that. Did I lose anybody at all so far? Or are we okay? We're doing okay? Fantastic. Okay, this is actually the figure here. So this is it binding in that pocket right there. You can see little tiny 23BPG. Okay, we sort of threw a little wrench in the gears, right? And right here we can actually see it. Here's the beta 1 subunit and beta 2 subunits right there. And you can see it actually binds between the beta 1 and beta 2 subunits. These right here are the amino acids that are directly involved in this binding. And see it's matching the hydrogen binding here. So it sticks and then it's stopping them from coming together. Okay, what time is it? Okay, we'll stop at this one. Fetal hemoglobin. Check it out. You can read it, and we'll start here next time, okay? All right. So, man, we did a lot in this course so far.